Hi, I'm Chris. I'm going to talk to you today about some work that we've been doing, a big collaboration between LBNL, UCB, and UCSF, using basic neural networks for neuroscience, both for data analytic tools and as brain-computer interfaces. So the generation of the vast array of speech sounds that we all produce are accompanied by the precise and rapid coordination of the vocal tract articulators. For example, production of the sound ba is produced by the contraction of the lips, da by the front tongue to the back of the top of the mouth, and ga by the back of the tongue to the roof of the mouth. To understand how the human brain produces these sounds, we conducted studies in neurosurgical patients implanted with grids of electrodes directly on the cortical surface. This is a grid of about 88 electrodes on the part of the brain that controls the vocal tract. Here are some example direct neural recordings from the cortical surface during the production of ba, da, and ga. The only thing I want you to take away from this is that there's a spatially and temporally complicated patterns of activity that are partially overlapping between these different sounds, but also distinct between these different sounds. Now, we wanted to investigate deep learning as a tool for understanding the nervous system. I think this is a good idea because neuronal activations are nonlinear, as are the processing elements in these networks. Also, deep networks can learn, by the definition, deep representations. However, we are in the regime of relatively small data. We're scientists, not machine learning guys. So we don't have 10 quadrillion examples of MNIST. We have on the order of 1,000 samples. And that's typically the case in experimental science. So I'm not going to go over this list, but the guy who actually did this, who just asked the question, Jay yesterday, basically used every trick in the book to get these networks to work. In particular, we used Bayesian hyperparameter optimization to optimize all these properties of the network. The basic results are as follows. So with these networks, we're able to classify our speech sounds with very good accuracy, in fact, state-of-the-art. Here we're looking at the raw classification accuracy for consonants, bold over chance, because chance will be differing between different categories, and the information transfer rate in bits per second. This is for one of the 19 consonants. This is for the 3 vowels. Most interestingly, we find that our ability to classify speech sounds was largest or was greatest when we looked at all 57 consonant vowel syllables produced. We were able to get 23 times over chance. For us, we interpret this as that speech control is not just the concatenation of these invariant tokens, but instead reflects a smooth trajectory through the phoneme sequence. To gain more insight into the data, we kind of looked at the confusion matrices that the network was making. Here we're looking at the confusions between the target syllable that was actually produced and what the network said was produced. If it was perfect, it would just be a black line along the diagonal. Here we see that network made errors, but that there was clear block diagonal structure to this matrix. Indeed, when we just kind of apply hierarchical clustering to this data set, we observed a rich hierarchical organization of phoneme features that was linguistically meaningful. I'm not going to go over the details of this hierarchy for time, but suffice it to say, it kind of agrees with some of the results that Surya did not quite get a chance to talk about, in the sense that the features that would correspond to the largest eigenvalues of the data matrix have are at the top, and you can kind of go down the hierarchy in that way. Now, moving forward, we want to kind of move away from this categorical description of speech production and go towards more a continuous representation. Here what we're doing is some data that I collected in the clinic. This was a woman that was, again, implanted with an array of electrodes, and she very graciously allowed us to paint her lips and kind of do this kind of Rocky Horror Picture type of videos. With this data and just kind of straight up, dumbass linear decoders, we can kind of decode quite well the kinematics of, say, the lips. So what we'd like to kind of do is to use Spiking Neural Network Kalman filters to kind of track the movement of those articulators in real time. Just as a proof of principle that we can do this, we kind of implemented just a very simple Spiking Neural Network Kalman filter to track a cannonball This is kind of following the work that was done at Stanford a while back. The long and the short of it is that you can see that all these lines are overlapping quite tightly, demonstrating that our spiking neural network Kalman filter is tracking the z trajectory of this bow cannonball quite well. What we'd like to then do is use neuromorphic hardware, such as the IBM True North chip, towards a low-power, real-time neuromorphic computing system for brain-computer interfaces, where the low power is really critical. Right? We can't be toting around a supercomputer behind us if we want to have a real brain-computer interface. Our strategy is to first do a classification across broad categories and then define specific trackers that will kind of predict the movement of articulators with high resolution. As it turns out, the brain and the Large Hadron Collider are pretty similar in the following sense. So one of the big challenges that is posed by this big machine is to track the millions and millions of particles that are produced by these various collisions. And the basic strategy that we can imagine taking is, again, do a classify then track type of an approach, again, with low-power computing hardware. And with that, I'll kind of conclude. I'd like to thank the people that actually did the work. Jesse Levizzi is a graduate student at UCB who did all the deep learning work. And then Paolo is a researcher up at Alvin Nindell who did the Spiking Neural Network Kalman filter. And Edward Chang is the neurosurgeon at UCSF who collected the data. Thank you.
Thank you.